Um, we're looking at what happens when you run a random process through a linear system, characterize the output. Now we're going to talk about the output over all time, not just out in steady state as time goes to infinity. That was called stationary analysis. Now we're going to talk about transient analysis, which is output over all time. Well, back when we talked linear systems, we had this basic relationship. In the Laplace domain, the output was the product of the transfer function and the Laplace transform of the input. And from what we know about Laplace transforms, that means in the time domain, the output is the convolution of the weighting function and the input. Convolution is commutative, so either one of these works. This g was the weighting function, which is the inverse Laplace transform of the transfer function. Here's this. So let's start looking at the output. First thing we look at is the mean. Here's the output using this formula. Mean is the expected value of that output. Means take the expected value of this. And like we did before, we can move the expectation operator inside the integral. Expectation is a linear operator, and integration is a linear operator. Nothing random in these limits of the integral. And g itself is not random, but the input is random. So the only thing we really take the expectation of is the expectation of the input. And we're assuming throughout this module that the inputs here are wide sense stationary. Which means this expectation is just a constant. Out of the integral, and here's what we have. In general, this integral is going to be some function of t. When we did steady state analysis, that was not the case. But anyway, we have a formula for the mean of the output. Let's look at an example. Basic first order system, which means the weighting function, go to your Laplace table, and here's what the weighting function is. The expected value of that guy by the formula is going to be whatever the mean of the input was times this integral. And now we have what the g of tau is, so we put that in the integral. And take that integral and this. This is a function of time, not just a constant. In fact, it's an exponential increasing thing that asymptotically approaches the mean of the input. What about the autocorrelation function? And from that, we could get the mean square value, right? And we have this formula in general, output related to the input. Autocorrelation function is this expectation, the product of two signals. The expectation, and here's what those two signals are. We'll change the variable of integration because we're going to combine them into one double integral. We have this, and again, we can move the expectation operator inside. The only thing random are the inputs. In general, this expectation is the autocorrelation function of the inputs with two arguments, but since we assume it's wide sense stationary, it's a single argument where it's the difference of these two arguments. So I can say it's t sub 2 minus v minus this, t sub 1 minus u. You get this. That's because it's wide sense stationary. So we have a formula for the autocorrelation function of the output. The mean square is when both time arguments are the same. Put in t and t here, which means this thing goes away and it's just the autocorrelation function, this u minus v. So now we have formulas for the mean, the autocorrelation function. An example of finding the mean squared. Here's our differential equation. X dot is, which means our x is the integral of the input. The output is the integral of the input. If you look at its subsidiary equation, you get this, which from there we can determine the transfer function, and it's just 1 over s. This is the transfer function, simple integrator. And notice something, it's not stable. This has a pole at 0 at the origin, which is not strictly in the left-hand plane. This is an unstable system. Remember, in stationary analysis, we couldn't analyze unstable systems. And anyway, in this example, we'll say this is the autocorrelation function of the input, which is something Gaussian process. Markov, Gauss-Markov process. And we're just finding the mean square, not the whole autocorrelation function. So here was the previous sheet. And in general, what it was, and here it is in our case with that autocorrelation function. So now it's just, this problem just amounts to taking this integral. And what's the region of integration? It's this square in the UV plane, two variables of integration, both up to t. And we got to split it up because of this absolute value. Let's see, if I do the bottom one, I'll probably integrate over, I guess, v first. I'll go from 0 up to u. And u will go from 0 to t. This upper triangle, I'll probably integrate over u first. From 0 to v. Let's see if that's how I do it. Yeah, I think that's how you do it. So here's the lower triangle, here's the upper triangle. And it takes a little doing. I had to figure this off to the side. But these two double integrals are actually the same thing. You do a couple of change of variables here, you can convince yourself that they're both this integral. So the sum of these two is just 2 times what the 1 is. So the rest of this is taking an integral. I can pull out the v part. I'm integrating over u first. So I can integrate e to the beta u. Easy enough, right? I get this. I got to integrate over v. It's kind of a tedious little integral to do. I'm not going to go over every step here. Freeze this chart here if you want to look at the actual integration. And you get kind of this ugly thing for the mean square. It's a function of time, t. And if you look at this, even as time goes to infinity, you can take the limit as time goes to infinity. You still get it's a function of t. It never settles to some constant, not even in steady state. There is no steady state. It just keeps growing as time grows. Remember, this was an unstable system. I'm going to really save this one for another video. And the reason is it's going to lead to integrals that involve the Dirac delta function. We touched on that before, but it's kind of a difficult subject. My students had difficulty with it. You have to be careful. We're going to use the sifting property of the Dirac delta function. So I'm going to save that for another video. But anyway, we have those three formulas for the mean, autocorrelation function, and square value. For all time.